Hello, I'm Mike McCulloch. Today I'd like to talk to you about the Dynamical Casimir Effect. So the normal Casimir effect I've talked about before, but that's caused when you have two parallel metal plates and you put them very close together. So everywhere there are quantum fields, quantum particles, quantum waves, and outside the plates any wavelength of these waves can exist. So there are lots of waves outside the two plates, but between them, only the waves that have nodes on the plates can exist. So fewer waves can exist between the Casimir plates. So this means that there are more quantum waves pushing the plates together than there are inside them pushing them apart. So they tend to move together, and this has been seen in many experiments. But in 1970, Gerald Moore suggested the Dynamical Casimir Effect, which is similar, but instead of having two plates, you just have one and you waggle it about in empty space. Now, what this does is that whereas the twin plates of the Casimir Effect damp the vacuum between them, the lone mirror, or metal plate if you like, as it's being moved around, it encounters variations in the quantum fields, and the electrons then within the metal or the mirror have to move to cancel it. And just like in an antenna, you get electromagnetic radiation coming off and the production of photons. So this was predicted by Gerald Moore. And it was first seen in 2011 by a Swedish team led by Wilson. And they published it in this paper here. And they used a very interesting device called a squid. So this is a superconducting quantum interference device that looks a bit like this. So you have a transmission line, the horizontal line, then there's a conducting loop with two Josephson junctions shown here by the black rectangles, and Josephson junctions are very interesting. They're composed of, a bit like capacitors, but composed of superconducting plates close together, as shown here, with an insulator between. So they force electrons to jump across a gap with very high acceleration. So it's very interesting that this is similar to the capacitor tests we and others have been doing. Josephson junctions are very interesting things. So Wilson set up this system with the loop and the Josephson junctions, and then they varied the magnetic field across the squid so that this effectively varied the length of the transmission line. It varied the inductions of the system and effectively the length of the transmission line. So this was a way to mimic the fact that you're moving a metal plate very fast. And in doing this, we're able to effectively move the metal plate to about 10% speed of light, at that speed. So they did it this way because it's impossible to actually move a real plate that fast and vibrate it that fast, because it would break. It would not be physically possible. So this was a way to do it. And then they observed photons coming off. Just as I said, their explanation was that this was creating a sort of aerial system which would emit electromagnetic radiation. And they saw photons, electromagnetic radiation, coming off with a wavelength of about 0.4 meters. But as I always like to try and do, there's an alternative way to understand this. The motion of this mirror, or this effective mirror, has a particular acceleration associated with it that you can calculate in this way. So the acceleration of the mirror is 2 times its velocity times the frequency of it. And the frequency was about 10 gigahertz that they used, and the velocity it got up to was about 0.1 c, 10% speed of light. So if we put these numbers in, we get that the acceleration of this mirror is 6 times 10 to the 17 meters per second. And so, okay, could these photons be thought of as being Unruh radiation, which would be nice and would bring this in line with QI? Well, yes, it can, because the wavelength of Unruh radiation associated with that acceleration is given by lambda u is 2c squared over a, where a is acceleration, and that's 0.3 meters, which agrees with the 0.4 meters that they observed. So, and I've actually emailed Wilson about this, and I got a positive reply. One way to think about this is that this is Unruh radiation coming off. And so this is similar in a way to some of the propulsion schemes that quantized inertia may provide. And if we could increase the frequency of this system, we might be able to boost the potential thrust we might get from such a system. Okay, so I hope you've enjoyed this short, and you're impressed with the dynamical Casimir effect, which is in fact a beautiful thing. And I look forward to speaking to you next time. Goodbye.